All right, we're going to look at how to solve these separable differential equations. First of all, what makes them separable is the fact that once you kind of separate the differentials, which really all we're going to be doing is moving this dx up over to here, right? And on this one, the dt up over to here. Um, Once we do that, then we want to use factoring, multiplication, division, those kinds of operations to get the y's with the dy and the x's with the dx. If you can do that with those types of operations, so that you have like a function of y times dy equals a function of x times dx, then it's a separable differential equation, and we can solve it with separation of variables. So that's what we're going to do on these two. These are both separable. So I'm going to get 18 out of the way for now, and we'll come back to it in a minute. And let's look at number 12 here. So we have, again, the first step there is to kind of separate the differentials. We have dy dx equals natural log of x over xy. So the first thing I'm going to do is rewrite this, but with the dx up here. Now, I'm not going to say multiply both sides by dx. That's problematic because dy and dx on their own are called differentials, and a differential is infinitesimal. It's approaching zero, and it's bad business to be multiplying both sides of an equation by an infinitesimal. So we aren't technically multiplying here when we move the dx up there. However, these two equations are equivalent to each other. Just real quick, this says dy dx, which is like the rate at which y changes relative to how quick x changes. So dy dx is equal to natural log of x over xy. One way to kind of read that is y is changing natural log of x over xy times as fast as x is changing, right? Because you can think of this as like a ratio of rates of change. Well, this says the same thing. Y is changing natural log of x over xy times as fast as x is changing. So anyway, once we do that, now what we need to do is, like I said, separate the variables. So I have a function of x here times dx. That's great, except that I have this y that's kind of in the way. So all we're going to do is use some algebra here to get that y over here with the dy. We're just going to multiply both sides of this equation by a y, and that'll do the trick. So now what we have is y dy equals natural log of x dx. Sorry, natural log of x over x dx. And the next step at this point is just to integrate both sides. So we have y dy, we'll take the integral there, equals the integral of natural log of x over x dx. And what we want to do now is solve this equation by first integrating. And ultimately, we're trying to solve for y. Just kind of keep that in mind. So for example, if I had any kind of constant multiple here, like a 2 or a k or something, my inclination is always to leave any extra stuff on the x side if I have a choice. Because if I know I'm trying to isolate y at the end, it just makes more sense to kind of keep the y side as simple as possible, generally speaking. So anyway, when we integrate on the y side, we're just going to get y squared over 2, right? You do the power rule there. And you might be thinking plus c, and that's fine. You could put a plus c here, but I'm going to save it. We'll talk about that in a minute. I do need to do something over here, though, right? You might not know the antiderivative of this off the top of your head, but we can do a u substitution. If you let u equal the natural log of x, then your du is 1 over x dx. And hey, that works out perfectly. If you're not really clear on the u substitution stuff, you should probably look back over that stuff. I probably have some videos on that you could look at. Or you can look through the textbook and practice that as well. So anyway, when you do that, we get natural log of x, that's my u, 1 over x dx, that's all du. So it's just the integral of u du. And that's going to get me u squared over 2, right? I'm not even going to write u squared over 2, though. In the interest of space, I'm going to go ahead and sub the natural log of x back in there. Natural log of x squared over 2. Now I'm going to put the plus c over here. Again, on the left side of the equation, I have y squared over 2. Just going to clean that up a little bit there. And yeah, now we're in business here, right? Now we've got an equation, and there are no more integrals to do. The plus c. So we could have put a plus c over here. Both integrals get a plus c, but they're different, right? So maybe this has c1 and this has c2, and then if you subtract c1 over to the other side, you get c2 minus c1, and what's that? It's just another c, right? So this c kind of covers both of them. And even this step's correct because this indefinite integral still has, an unspecified constant of integration in it. Like once we integrate, we know that's there. So we're actually still technically correct at this step as well. All right, anyway, we're going to kind of move up here. And what I'm going to do now is multiply both sides by 2, right, to get rid of the over 2. That'll be my first step at this point. And I'm going to see something here with the c that we can do. So when I do this, I get y squared equals, on the other side, natural log of x squared over 2. That over 2 cancels with the 2 that we multiply, right? They reduce to a 1. So we get the natural log of x, quantity squared. And then you might be thinking plus 2c, and absolutely, that's true. But again, c is an unspecified constant, so 2c is just some other unspecified constant. Some people, when they do this, they like to change the c every time they do it. So you could call it like c1 and c2 or whatever. You don't need to. I don't know if you have a teacher or professor in the future who is picky about that. They may ask you to, but a lot of books, a lot of teachers, a lot of professors, whatever, multiply unspecified constant by 2, what do you have? You still have an unspecified constant. It's a different one. We need to be aware that this c is not exactly the same as this c, but that's fine. Anyway, our goal was to solve for y, so we are now going to take the square root of both sides. And when you do that, the square root of y squared isn't actually just y. It's actually the absolute value of y, right? Because it can only come out positive. So you want to be aware that you're used to doing a plus or minus, right? When you do square root of both sides, that's of course why we do it, because that absolute value piece. And so when you write this, it is actually plus or minus the square root of the natural log of x squared plus c. All right, so this is called our general solution right here. This is not the final answer to this question, because we still have a little more to do, but this is called the general solution. But we have a little more information we haven't used yet. This is called an initial condition. And what you do with an initial condition, just like we did when we were doing just regular antiderivatives, right, is you can plug the initial condition in for x and y to solve for c to get what's called a particular solution. One thing I want to be very clear about on differential equations, when you get a particular solution, you only get one continuous piece of curve, right? So right now I have this plus or minus, which gives us multiple, and the plus c, of course, gives us all these different curves. When we plug this in, we're going to narrow it down to just one curve and one continuous stretch of a curve, actually. We can't, include two different parts across a vertical asymptote, for example. No, once you hit that asymptote or a hole or anything like that, it stops. All right, so I'm going to plug in 2 for y and 1 for x, and I'm going to get 2 equals plus or minus the natural log of 1, which is, well, that's 0, right, squared, plus c. And a couple things here. First of all, that plus or minus, I don't need it anymore. This square root is going to equal 2, positive 2, not negative 2, so it can't be minus. That's what I'm saying when I say it's only going to give me one continuous piece of curve here. we no longer need the plus or minus. Not for it's part of the general solution. It will not be part of this particular solution. It's just going to be the positive. Now, if this was y of 1 equals negative 2, then I would only keep the minus. So I would just, get rid of, I would replace the plus or minus with a negative in that case. All right, so I need to know what c needs to be, and you can probably tell c is going to be 4, right? Because the square root of 4 is 2. Of course, you can solve it algebraically. If you don't see that right away, you can square both sides. C equals 4. And so our final result here is y equals, again, the positive square root, not plus or minus. And then we have the natural log of x, quantity squared, plus 4. That is my particular solution. Okay, I'm going to go ahead and move on to number 18 now. Very similar kind of a question here. This one we have L and T instead of Y and X, but we handle it the same way. It's helpful to just kind of keep in mind what your X and Y variables are. Big L is our Y variable, right? Think like dy dx. T is our X variable. We're pretty used to T being an X variable, so that's helpful. Again, first thing we're going to do is move the dt up here. So I'm going to write this as dl equals kl squared times the natural log of t dt. And the next thing I'm going to do is put any l's with the dl, and there's really just this l to the second. So I could divide both sides by l squared, or you can think l to the negative 2, right, when you move it over, which is handy because we are going to integrate, and the power rule is what we're going to be using, right? So L to the negative 2 dl equals k natural log of t dt. And again, I mentioned this last time, that k, it's a constant, it's unspecified. I want it on the t side, right? Like I'm solving for L. L is my y variable, so anything extra I'm just going to keep over here. I'm going to take the integral of both sides, and I'm going to do the power rule. L to the negative 2, when I add 1 to it, I get L to the negative 1. And, of course, divide by negative 1, so it's negative. Equals, and then on this side, I need to figure out the antiderivative of the natural log of t. Interestingly enough, I didn't vet this question fully before I signed it for my AB class here, so I will just mention finding the antiderivative of natural log of x, or natural log of t in this case, is something that can be done with integration by parts, which is a Calc 2 or Calc BC topic. It's not in the AB curriculum. I'm just going to share with you guys what the antiderivative is without going through the process right now. It's not too hard to do, but here is your antiderivative rule for the natural log of x. It is x natural log of x minus x. So we're just going to go ahead and use that. Don't worry about it. Again, it will not show up on the AP Calc AB exam. It is something when you do integration by parts in Calc 2 that you will learn. So we'll go ahead and use that antiderivative. The k, again, is just a constant multiple. So our antiderivative of natural log of t is going to be this, but with t's. You might have been thinking, wait, isn't it 1 over t? And the answer is no. The derivative of natural log of t is 1 over t, right? The antiderivative of 1 over t is the natural log of the absolute value of t, right? Okay, anyway, we get k times t natural log of t, and then minus t. That's all in parentheses. So I'm debating whether I want to keep it in parentheses here. I'll go ahead and do that. Or if I wanted to distribute now. We'll do this though. And of course, plus c, right? You do need a constant of integration somewhere, but you don't have to do it on both sides like we mentioned before. We're trying to solve for L, so you want to keep in mind this is negative 1 over L. Again, we can multiply the negative on both sides. I'm going to go ahead and write this as 1 over L at that same step. I'm also multiplying by negative 1. When I do this, I'm going to get negative k times t natural log of t minus t plus c. And, a couple things here. One, you probably noticed I just went ahead and let that plus c absorb the negative, right? We haven't found c yet. There's a c value. We're going to find it, right? We're going to use this initial condition to find c. And since we haven't done that yet, it's okay. Like I can just let the plus c get multiplied by -1, and it's just a different c now, right? If this c was like +7, then this one would end up being -7, right? Maybe you're wondering, though, why can't the k do that? And the reason here is this k is also a constant, and it is unspecified, but the k needs to stay consistent throughout the problem. K was there at the beginning of the problem, and so k will be there at the end of the problem, and I want the k at the end of the problem to be the same k as the k at the beginning of the problem, right? So like if it means something, right? If this is like a formula for something in a physics problem or whatever, that k needs to be the same thing. C is different. I came up with c in the process of integrating, and I'm going to figure out what c is for this initial value problem. So I can screw around with c a little bit on the way here, and it doesn't matter. Once I plug in L of 1 equals -1, that's when I lock in c, and that's when I have to be more careful. All right, let me get this out of the way. Here, we'll just drag it down to the trash. Oh, it doesn't like it when I use this. Here we go. And anyhow, how do you solve for L when you have 1 over L? Well, you can just take the reciprocal on both sides, right? You can flip them, or you can think like multiply by L, divide by everything else. Same idea. Get out of my way. There we go. And back to my pen. So if we do that, if we take the reciprocal of both sides, we will have L equals 1 over that negative, by the way, I could just keep the negative on top. And then on the bottom I have k times t natural log of t minus t, and then plus c. Can I put that plus c? Does it have to be under the fraction here, or could I just put it out here? You might be thinking, hey, 1 over c, that's a different c, right? That's another constant. And that's true. If all I had was c and then I got 1 over c, I could make it into a different c. The problem is that's not all I have. This c is added to this stuff, and I'm taking the reciprocal of the entire side. And algebraically speaking, you can't separate this fraction with the denominator there. You can't make it like something over this plus something over c. It doesn't work. There's no algebraic property that we can use for that, at least not easily. So anyway, we're going to leave it there, okay? The c can only absorb things that it makes sense for it to absorb, where if it does this, it'll still just be another constant. So you do still have to be careful algebraically speaking. Anyway, we're going to go ahead and plug in 1 for t and -1 for L. And when we do that, we will get -1 equals -1 over k. And now when I plug 1 in for t, I'm going to get 1 times the natural log of 1. Hey, that's 0, right? Natural log of 1. Minus 1, and then plus c. So I'm going to solve for c. And this is -k, right? Plus c. That's what my denominator is. Let me just kind of replace that. And so I have -1 equals -1 over -k plus c. Maybe you could just look at this and think, okay, my denominator needs to be 1, because then I'll have -1 equals -1 over 1, right? That works. Or if you want to multiply this up here and then divide by -1, that works also. Anyway, either way, you're going to get c minus k equals 1. That's where this is headed. And so c equals, when you add k to both sides, k plus 1. And remember, k was present at the beginning of the problem. K is going to be present at the end. It is okay to replace c with an expression involving k. In fact, we need to. And so k plus 1, that's going to be my c value. So I'm going to go ahead, and with this value for c, I'm going to rewrite my function now. L of t, whoops, equals, again, this function with k plus 1 in for c. If you did it slightly differently, algebraically, and you have a different form, but it's the same, it's equivalent, of course that's okay. It doesn't have to look like mine, as long as it's equivalent. Maybe you don't have the factored part here. I don't know. But there we go. That is the particular solution to this initial value problem. This is the general solution here. And that's all there is to it.